in the last video, we saw that if we started with a massive star about 9 to 20 times the mass of the sun, and when it finally matures, the remnant of the star is roughly, or that remnant core of the star is roughly 1.5 to 3 times the solar mass, or the mass of the sun, then this remnant right here, and let me just be clear, this 9 to 20 times is the mass of that star when it's in its main sequence. This 1.5 to 3 times is the mass once it's shed off a lot of the, outer material of the star, and this is really the mass of the remnant of the star, kind of the core of the star. But at that remnant, once it stops fusing, once it stops having outward pressure, and once it has enough density, this, we saw in the last video, will cause a supernova. It'll cause a shock wave to move out through the rest of the material and essentially cause it to blow up. And this will condense into a neutron star. Now, in this video, what I want to talk about is, what if we're starting with a star that has a mass more than, and this is give or take. We don't know the actual firm boundaries here. But what if we have a star that is more than 20 times the mass of the sun? And this is kind of the original mass before the star burns itself out. Or when that star has kind of reached this old age, once it has that iron core, it has more than, so I could say the remnant, the dense remnant has more than 3 to 4 times the mass of the sun. And remember, it's going to have it's going to have 3 to 4 times the mass of the sun, but it's going to be far denser. It's just going to be a core. It's going to be an iron nickel core that's no longer fusing. So what happens to these stars? So it turns out that these are so massive that even the neutron degeneracy pressure will not be enough to keep the mass from imploding. And these stars, all of the mass in these stars, will just keep imploding. So in the neutron, so we imagine the first and kind of sun-like stars, things would collapse into white dwarfs. And maybe I should draw that in white. So they would collapse into white dwarfs. No, that's not white either. There you go. They would collapse into white dwarfs eventually. So this is a white dwarf. White dwarf. And here, the pressure that's keeping this from collapsing further is electron degeneracy pressure. The atoms are squeezed so much that the electrons are essentially keeping them from squeezing anymore. But if the pressure gets large enough, then you have the neutron star. So you have even more mass and even a smaller. And I'm not drawing this to scale. Neutron stars are tiny. White dwarf stars are on the scale of an Earth-like planet. Neutron stars, we learned in the last video, are on the scale of a city. So they're super dense, super tiny. And this has more mass than this over here. In fact, maybe I should just draw it as a dot, just so you have a sense of how dense it is. It's really just like one big atomic nucleus. Or, well, it's still small, but it's the size of a city. It's like a nucleus the size of a city. But this right here is a neutron star. Neutron star. And what's unintuitive about what I'm drawing is each of these smaller things have more mass. This overcame the electron degeneracy pressure to collapse even further. But if the mass is large enough, and this is what we're talking about in this video, even the neutron degeneracy pressure will not be able to keep that mass from collapsing. And there's even theoretical quark stars where the quark degeneracy pressure, but if you get even beyond that, then it all collapses into a single point. And I'm simplifying here, but it collapses into a single point of infinite density, infinite mass density. And this is really the mass of a black hole. And I'm calling it the mass of a black hole because there's different ways how you can view where a black hole starts and ends, or what exactly is the black hole. So this is all the mass of the black hole. Or we could say of the original star. So when we're talking about that remnant being 3 to 4 solar masses, all of that mass is now being contained. Well, not all of it. Some of it was released as energy during the supernova, and that was also true of the neutron star. But most of that mass is now being contained in this infinitely small point. And you'll hear physicists and mathematicians talk about singularities. Singularities. And singularities are really points, and even in mathematics, where everything breaks down, where nothing starts to make sense anymore, where the mathematical equations don't give you a defined answer. And this is a singularity because you have a ton of mass in an infinitely small space. You essentially have an infinite density right here. And this is hard to visualize, but you have kind of an infinite curvature in space-time right here. And I can't visualize that. So maybe we'll think about that in more videos. But the reason why I said that there's different ways to think about where a black hole is or where it starts and ends is that this is where the mass is. So, and if there's any other mass that was over here, it would obviously be attracted to this mass and then become part of that singularity. It would add to that mass, that already huge mass that's in an infinitely small point in space. But the reason why the boundary is hard to define is because there's some point in space around that singularity at which no matter what that thing is, no matter how much energy that thing has, it will not be able to escape the gravitational influence of the black hole, of that ultra dense mass. So even if it was electromagnetic radiation, even if it was light, and even if it's light that's shown away from the mass, it will eventually have to go back. It will not be able to escape the gravitational influence. And so the boundary where if you're within that boundary, that's really a sphere, so that boundary around the singularity. And that boundary around the singularity where if you're within the boundary, no matter what you do, no matter if you're electromagnetic radiation, you're never going to be able to escape the black hole. If you are beyond that boundary, you might be able to escape the black hole. So this guy could escape. This guy over here, no matter what he does, is going to have to go back into the black hole. This boundary right here is called the event horizon. This right here is the event horizon. Another word used in a lot of science fiction movies, and for good reason, because it's fascinating. And we'll actually learn in future videos, hopefully about Hawking radiation. We'll see that that is not radiation from the black hole itself. It's the byproduct of quantum effects that are occurring at the event horizon. But the event horizon is just this. It's this kind of point in space, or the sphere in space, or this boundary in space. Anything closer than or within the event horizon has to eventually end up in the singularity, contributing to that mass. Anything on the outside has a chance of escaping. So what would a black hole look like? Well, not even light can escape from it, so it will be black. It will be black in the purest sense. It will not emit any type of radiation from the black hole itself, from that mass. And so here are some depictions I got from NASA of black holes. And so just to be clear, what's happening here? What you're seeing here is black. That is not, you can view that as the black hole. When people talk about the black hole, that's often what they're talking about. But there's a point of infinite density at the center of this black sphere right here. And what you see is that black sphere. That really is the boundary of the event horizon. So this right here is the boundary of the event horizon. And what we're seeing right here is the accretion disk around the black hole. As all of this matter gets closer and closer to it, it's being squeezed more and more. It's moving faster and faster and getting hotter and hotter. And that's why the way this art is depicted, it looks like this stuff over here is redder and hotter than the stuff further out. It's just accelerating as it approaches that event horizon. Once it's in the event horizon, we cannot even see the light that it's emitting, even though it would be, starting to become unbelievably energetic. Here's some other pictures. This is a picture of a star being ripped apart. Not a picture. This is actually an artist depiction. All of these are artist depictions. We never were able to get such good pictures of actual action occurring near black holes. These are artist depiction. But this is a star being ripped apart by a black hole. So this star is getting pretty close to this black hole. Already out here, where the star is, it's very strong gravitational attraction. So any mass, that's being emitted from the star in that direction is slowly being pulled into the black hole. So the star is kind of being ripped apart by the black hole. This is maybe a better depiction of it. This is the star at first, and once it becomes under the influence of the black hole's gravitation, it starts to kind of elongate and gets ripped apart, and its matter starts spiraling in closer and closer to that black hole. And then once it's in the event horizon, we won't even see it anymore, because even the light from that matter, that intensely hot matter that's entering into the black hole, cannot even escape the black hole itself. Anyway, hopefully you found that interesting. And I want to be clear. we still don't understand a lot about black holes. In fact, this whole notion of a singularity, the fact that all the math and all the theory breaks down at this singularity, is a pretty good sign that our theory isn't complete. Because if our theory is complete, we would maybe get something a little bit more sensical than just all of our equations not making sense at that infinitely dense point. Anyway, hopefully you found that interesting.